Okay, today we're going to talk about reaction mechanisms, and we'll explain what is meant by the mechanism of a reaction using the terms elementary step, rate determining step, and intermediate. We'll also be able to derive the rate law for a reaction that has a rate determining step, given that we have the elementary steps and their relative speeds. The quest that goes with this play pause is on reaction mechanisms. So a reaction mechanism, essentially all it is how we got there. So we know that our rate law is K times the concentration of one of our reactants, usually to some power that dictates the order. And we have a rate that tells us the change in concentration per second, but the pathway isn't always clear. With reaction mechanisms are hypothetical in that sense. There's a lot of different possible ways that we can get there, and we use the evidence that we have to establish some different pathways for us. So, like, for example, we have photosynthesis. We know the overall reaction here, but we know it takes several steps to get there. This is the balanced equation, but there are a lot of little steps that have to happen in between for this to proceed. So we know it's made up of several intermediate steps. Whenever we say intermediate, College Board likes to use the term elementary. So if you hear elementary steps, we're talking about intermediates. So a bunch of little steps along the way. Okay. Ooh. So one of the examples for a decomposition reaction we have here is the decomposition of hydrogen peroxide. This is a reaction that's spontaneous. It happens on its own, and I actually want to get some hydrogen peroxide and show you in class. Hydrogen peroxide is always stored in brown or black bottles that can prevent hydrogen peroxide from coming into contact with light, because light can actually speed up this decomposition process. So putting them in those containers prevents it from actually decomposing on its own. And it takes a fairly long time for this to decompose. However, it does go faster with a catalyst. So if we have a catalyst, we know catalysts can lower the activation energy, and it will speed up the reaction. Now, this is our overall reaction, right? So this is overall. Let's try writing that again. So this is our overall reaction. And with the catalyst, we can have a proposed hypothetical reaction mechanism. All right. So we have a slow step, and the hydrogen peroxide comes into contact with our catalyst, and it forms this intermediate here, OI minus. This thing doesn't truly exist. We're not really sure what it is. It doesn't follow normal bonding rules, but we can say that this might be something that forms in between. And that can be used in the next step. That complex can be used as a reactant and help aid in the decomposition even further, and we end up with H2O and O2, which is what we want. And the important part here is that our catalyst comes back out as a product. So the catalyst is both a reactant and a product. If we were to treat this like in a Hess law fashion, add these things together, our catalyst would cancel out, this intermediate step would cancel out, and we'd be left with our balanced equation. We've got 2H2O2, we've got 2H2O, and we've got our 1O2. So all this does, the catalyst, all it does is get used up in the reaction, but then it comes back out and it remains unreacted essentially. It just helps speed up the process. And then this is our intermediate, as I was talking about, OI minus. Okay. So, reaction mechanisms. The whole point of them is to show the relationship between the reaction pathway and the rate law. Because we've spent all this time looking at rates, and we know that the concentration and the order and the rate constant are all proportional to each other, but we don't really know why. So the reaction mechanisms just explain why the rate law is what it is. So the reaction mechanism is a series of elementary steps, and there are two requirements. First requirement is that the sum of the elementary steps must give the overall balance equation for the reaction. We just showed that in the last example with hydrogen peroxide. The other requirement is that the mechanism must agree with the experimentally determined rate law. Okay, so if we were to go back and look, we have a slow reaction and a fast reaction. And I'm actually going to add this one last thing here. The rate of the overall reaction is limited by and equal to the combined rates of all, let's just say elementary steps. Combined rates of all elementary steps, steps, I got a slight typo there. It's the rate of overall reaction is limited by and equal to the combined rates of all elementary steps up to and including the slow step in the reaction mechanism. So in our example, if I clear some of this out, we have these things labeled as fast and slow step. Well, our very first step is the slow step. So our reaction mechanism, our rate law is going to be built around this step here, right? Because this is what determines the rate determining step. We know that these two things don't exist truly because they cancel out down here. So we would not write them in the rate law. So we could suggest that our rate is equal to K times the concentration of my H2O2. Now, the temptation is to square this because there's two hydrogen peroxide molecules, but we're not going to square it because there's only one hydrogen peroxide in our rate determining step. We don't actually care about this in our rate law at all because we've already hit our slow step. Okay. So let's do, let's talk about intermediates more, and then we'll do another example of that. So with intermediates, they're just species that participate in the elementary steps of reaction, but they are not involved in the overall reaction, so they're not part of the balance equation. We have some more vocabulary. We have molecularity. So this is just the number of molecules that participate in atomic rearrangement. We have three types. We have unimolecular, we have bimolecular, and termolecular. The prefixes help explain exactly what they are. Unimolecular involves one reactant molecule. Bimolecular is involving two reactant molecules. So something to notice that since there's only one, this is a decomposition reaction. With bimolecular, this is a collision between two reactant molecules. The orientation matters. We'll talk about that a little bit more in the next play posit. And then there is one with three reactant molecules. It's termolecular, but this is pretty rare. We don't see this very often. Okay. The rate determining step is the slowest step. That's what I mentioned on the slide before. And we have catalyst, which goes in and does not show up in the final reaction. If you need to pause for a moment to write down the vocabulary, please do. Okay, so let's do an example. Oh, nope, not an example yet. Sorry. It's coming soon. So here's a nice table that puts together examples of a generic elementary step and what the rate expression would be. So for unimolecular, like I said, it's decomposition. We have one reactant and goes to products. This is a first order. The rate is equal to K times the concentration of A. With bimolecular, the overall order is 2, but it's still first order for each. You could have A plus B, and that would be bimolecular. And you get rate is equal to concentration of A times B. You also have another bimolecular where it's 2 of the same component, so 2 of your A molecules. That would be second order because it's the same component colliding with each other. Then termolecular, this is the rare one, and actually I think our first example is termolecular on the next page. You have 2 of A and B forming your products. Notice that, again, the coefficients do impact the rate law, okay? So here's our first example. We've got 2NO plus bromine gas, and we get 2NOBr. And the rate law is KNO squared, Br2. So this is a termolecular process. But since they are rare, it suggests that it has a 2-step mechanism. So our job is to show that the following mechanism for the above equation produces a rate law consistent with the experimentally observed one. So we're trying to figure out how do they get this rate law. Okay, well, we should add them together. And I'm going to number them. Actually, they're already numbered 1 and 2. When we add them together, we want to cancel out what we can cancel, and we want to combine the terms that we can. So NOBr is on the product side in the first step, and it's a reactant in the second step, so it gets used up. So it's not part of the final reaction. But we do have 2NO, we do have a Br2, and we end up producing 2NOBr, which matches our balance equation. Yay! Now, this is where the fast and slow step stuff comes into play. We said that the rate law is equal to the sum of the elementary steps up to and including the slow step. So we actually have to include both parts here, okay? So let's break it down. We could write a rate for our first elementary step. We could say our rate for the first one is K, and then the concentration of NO, the concentration of Br. All right. Then we can go to our second step. NOBr2 is not part of the reaction, so the only thing left is the rate is equal to K of NO. All right. So these are my 2 elementary steps. I'm going to label this as elementary. So these are the elementary rates. And to get my rate law, I just have to combine these. So the rate is going to be equal to K NO squared and Br. And that matches up with what I have here. So perfect. This is a valid mechanism. Okay. Let's do the next one. So nitrogen oxide is reduced by hydrogen to give water and nitrogen. I give you the overall balance equation here and a possible mechanism. Now this one, we're going to do a couple things with this. They want to know what the molecularity is of each of the 3 steps, and then it says show that the sum of these elementary steps is in the net reaction. So we want to show things canceling out, and we want to identify molecularity. So remember, we've got 3 types. We've got unimolecular, we've got bimolecular, and we've got termolecular. Okay. Now, we only want to focus on our reactants. How many possible reactants are colliding with each other here? This is the tricky part. There's only 1 reactant, but there's 2 molecules. So this first step is bimolecular. because there are two of the same particle. What about the second one? How many reactants are colliding with each other? Should have said 2. Alright, what about the third? Also 2. So the molecularity is bimolecular for each step. Now we want to take a look closely at these. They don't tell us which is fast or slow, so we can't actually determine the rate of reaction yet, but we can try and figure out which things will be in the reaction and which things will be intermediates. Okay, so I'm going to put a box around my intermediates. So 2NO, I want that to be part of my overall equation, but N2O2, that will be an intermediate. And I see that they're on opposite sides here. Those would certainly cancel out. My other intermediate would be N2O, because that is not part of my overall reaction, and they're on opposite sides. Those two would cancel out. Then I just need to combine like terms. I've got my 2NO, my 2H2, my N2, and my 2H2O. So that's all you need to do. It's kind of like Hess's law. Just show that the intermediates cancel out like they're supposed to, and then they agree with the stoichiometry, and it's good to go. On to the next one. Okay, so the balance equation for the reaction of gases nitrogen dioxide and fluorine is 2NO2 plus F2, and we get 2NO2F. Okay. 2NO2F. So it gives us the experimentally determined rate law, and we want to try and see if this is an acceptable mechanism. And it says, does it satisfy the two requirements? So let's go back. Our two requirements, hold on. Our two requirements as stated before. The sum of the elementary steps must give the overall balance equation for the reaction, and the mechanism must agree with the experimentally determined rate law. Okay. Whoa. Zoomed in a little too far. Where'd it go? This one. Okay. So, first we can figure out the sum. So, that's the easy part. What is one of my intermediates in this reaction? Should have said F. F is an intermediate. It occurs on both sides. F is going to cancel out. Alright. And when I combine the rest, I get my 2NO2 plus F2, and I get my 2NO2F. Okay. So in that regards, it agrees. Now we need to check to see if it matches our experimentally determined rate law. All right. So if we were looking at the overall equation, your initial reaction might be to say NO2 is second order and F is first order. Sorry, F2. That's an ugly 2. Why is this incorrect? Well, let's look carefully. We have information here that tells us that our first step is our slow step. So, if our first step is our slow step, our second step has no impact on my rate law. So I just need to look at my reactants here in my slow step. My rate law, if I'm looking at my slow step, rate is equal to K of NO2 and F2. And that matches up. So this is an acceptable mechanism. It satisfies both requirements, agrees with the stoichiometry, which is good, and it matches up with my experimentally determined step because the slow step defines my rate law. Okay. last one, let's try this one. Nitroamide N2H2O2 decomposes slowly in aqueous solution. This decomposition is believed to occur according to the reaction mechanism above. So determine the rate law for the decomposition of nitroamide that is consistent with this mechanism. Okay, so let's look at my overall steps. I'm told I have a fast, a slow, and a fast. So just by looking at this and using the given information, what are my intermediates in this reaction? Well, I've got a couple intermediates. Could have said that N2HO2 is an intermediate. Could have also said that OH is an intermediate. Now the question is, if I want to look at my rate law, oops, I'm sorry, I forgot one, there's one more. H plus is also an intermediate. So, if we want to look at our overall reaction, N2H2O2 yields N2O and water. Okay. Because all of my intermediates would cancel out. So here's my overall equation. I need to find a rate law that agrees both with this and agrees with my rate determining step. So when I go to figure out my rate law, which steps am I going to include in my rate law? Hopefully you crossed out number 3 because you saw that it came after the slow step. It does not matter. So we just need steps 1 and 2. So let's look at the rate of each of those. What is the rate law for step 1? Okay, hopefully you said rate is equal to K N2H2O2. All right, let's look at the rate law for step 2. What is the rate for step 2? This one's a little trickier. N2HO2 minus is an intermediate, so there are no reactants here. So the rate is equal to what? The rate is just equal to K here. So our first step is first order, our second step is 0 order. So if this has no effect on the rate, then my rate law is going to be K equals N2H2O2. That one's tricky. Now, this agrees with the overall stoic. We have our one reactant here. It accounts for the slow step, being the rate determining step. And we don't care about the things that happen after the slow step, because that is what limits our reactant. Okay. And let's see. That is all for reaction mechanisms. Pretty straightforward. Have a good night.